like to welcome all of you from my side too. So I would like to talk today about the opportunities that additive manufacturing offers in the supply chain of the aviation industry. Just to give you a quick overview what this project is about, it deals with the application of additive manufacturing in the repair chain for spare parts in aeronautics. The origin of funding is the EU FP7 framework program, and the total budget is round about 6 million euros. We have a consortium of 12 partners from all over Europe, and including small and medium enterprises, as well as industries like Boeing and Lufthansa, as well as research institutes like the University of Paderborn, which is also the coordinator of this project. We are now in the final project year of this project. Let's talk about some fundamentals. Currently, the existing processes do not contain an AM application, and they are not built to do so. This is why today excessive supply chain warehousing is necessary to enable such an effective supply chain as we have today in aerospace. Our goal is now to reduce the costs that accrue during this warehousing and the supply chain with the help of additive manufacturing. So we do not have to rely on the state of art for additive manufacturing to research this aspect, but we have to take into account future developments of the technology to be able to exploit all of the advantages that are offered by additive manufacturing. So our approach is with additive manufacturing as a flexible repair and production technology. It is possible to decrease the logistic costs, and thus with the different characteristics and approaches we will describe in this talk, we can have a look how we can use these benefits of additive manufacturing efficiently. This is based on some scenarios that we have developed where we identified sustainable business cases. So our main objective is that we want to decrease the lead time within repair and production of spare parts, and we try to get there with a higher automation level and with an improvement of every process step in this workflow. So you can see here on the above that we have the conventional repair chain with some semi-finished goods, warehouses, and the final part, and we have different process steps to get there. Our approach is to get from the raw material to the final part, and we also need several process steps, but we also try to enhance them. For example, in terms of quality, costs, performance, and so on, and of course the time. So the aerospace is very special industry. For example, the Boeing 747 has round about 6 million parts, and to produce them and assemble them we need round about 75,000 drawings. On the other hand, Airbus stocks around about 3.5 million spare parts and additionally 100,000 tools to produce them. In addition to that, we have the problem that the product life cycle is extremely long for the aerospace industry, up to 6 decades in this case. So if there is an incident, then we have to have the spare part at the gate or where the aircraft is located as soon as possible. So we have a really high demand on the supply chain. So you can imagine we have Boeing aircrafts, we have Airbus aircrafts, and different size. So how many parts do we have in total? I would say a lot. Let's take a look at this supply chain network. You can see this is a very complex network with several supply chain participants and logistics centers that are located around the world. So on the left, we have a few hundred suppliers with local warehouses somewhere, and we have this huge spare parts storages all over the world, supplying customers nearly in every corner of the world. As I mentioned before, we also have to take into account not just the state of the art of the technology, but to look forward and have to have a look where we can expect some developments. For example, in terms of the machine, we can expect to have bigger build chambers in the future, not just to be able to put more different parts in one build chamber, but also to be able to put bigger parts than today into the build chamber. And if the chamber size increases, then of course we need higher build-up rates, and the better accuracy will help to reduce the finishing effort as well. In terms of material, we need specific characteristics for aerospace, fire resistant and extremely rear resistant, whatever. Another important point could be that multi-material processing will be available. This would mean a substantial effort for additive manufacturing, as it will push it really forward. So we can have parts that consist of different characteristics, like a very tough inner core of the part and a rear resistant outside. There are some other aspects. For example, we need better software to build a bionic design. We need a certification procedure for additive manufacturing, as this is one of the major and important aspects in aerospace, and we need better interfaces so the operator can operate the machine easier. Now let's take a look at warehousing and the supply chain overall in aerospace, starting with different spare part classifications. So on the one hand, we have consumer parts that are consumables and expendables. For example, oil, brakes, wheels, and so on. They are used up and have to replace at some time, but this is mainly predictable demand. So we can put them in inventory, and we know this will be used sometime. On the other hand, we have cycle parts, where we have the rotables and repairables, and here we have a much higher degree of unpredicted failures, up to 80%. These 80% are not necessarily aircraft on ground incidents, but occur during a normal maintenance event, but still they are unpredictable. Furthermore, we have the line replaceable units, the shop replaceable units, which are often having a high value, and this is where we have high warehousing costs. And if we have an aircraft on ground, this has highest priority, and then the part needs to be at the aircraft as soon as possible. On the right side, we see the figure having the out-of-stock costs and the storage costs. Together, if we have nearly no storage cost, we will have extremely high out-of-stock costs, and otherwise vice versa. So there will be a minimum point where we have a specific service level, which is still having high logistic costs. If we now apply additive manufacturing to that, we can reduce both costs and get to overall lower costs, logistic costs, and maintaining the same service level. So the main goal within the aerospace supply chain is to satisfy the needs of the customer as the aircraft needs to be in operation to generate earnings, and so the MRO provider and the airline is interested in keeping the airline airworthy. The operation time is now a key factor, so we have to have regular maintenance events to keep the aircraft airworthy, and so the MRO provider is not just a business partner, but it's more a cooperation. Overall, it is the aim to minimize the costs of this whole process, but still we have a very volatile demand, so we cannot predict the failures, and so we need excessive storage and a fast reacting supply chain to be able to supply the required spare part. Additionally, we have high part value, and as I mentioned before, this extremely long product life cycle of 60 years, where we not just have to provide spare parts, but also stock the correspondent tools to produce spare parts. Overall, this leads to extremely high inventory costs, as we can see on the next slide. Here's a further breakdown. The quality and safety standards, they are the reason for the high part value, and it's approximately 20 to 30 billion US dollar worldwide for the spare parts in stock. And it is approximated that around about 22% of this value is the annual worldwide cost for just storing the spare parts. And you can see here 20% of this $5 billion have to be accounted for obsolescence, damage, and a new certification. 30% are for the storage itself, if you have to pay for the documentation, insurances, and taxes, and so on. And 50% is just capital lockup. So if we can decrease this part value, then we can have extremely high cost savings. Here we can see on a general view the supply chain in aeronautics. We have the customer, the airline, that monitors the use of its aircrafts and the components installed in them. And we have maintenance events where we need to replace a spare part. So an order is given for replacement and sent to the supplier. The warehouse ships the spare part to the warehouse of the customer, and then it is installed, and the cycle begins from the beginning. To be able to supply the spare part, the supplier needs to forecast the material, and as I said, it's an extremely volatile demand, so he has to produce spare parts beforehand and in batches, so he might have a high inventory to do so. With additive manufacturing, this can become much more flexible, as we can produce nearly on demand and do not have to stick to batches. So depending on the product type and the supply chain requirements, there are mainly two approaches that have to be considered in the supply chain. The lean approach is mainly focused on the elimination of waste, such as wrapping and transportation costs and so on. The reduction of failures is an important issue, either during the manufacturing process or the complete order and delivery process. Overall, it is aimed to get to efficient processes. This is mainly true for functional products that are predictable in its demand. The agile approach has its main goal to reduce the lead time by offering a high flexibility, so a fast reconfiguration of the manufacturing processes is possible. The availability should be high, so it can react short-term to sudden demands, and this is most suited for innovative products with a volatile demand. So how does AM influences the supply chain? Additive manufacturing combines the two approaches with being a lean manufacturing technology and offering a high flexibility due to the fact that no shaping tools are required. Warehousing and the shipping of finished and semi-finished goods can be significantly reduced, as only raw material has to be available and nothing else. As it is able to produce also complex products, we can reduce the handling effort for several parts, as they can be reduced to one part, as we have heard today earlier in the keynotes. So we save here processing steps. Additionally, we have a reduced setup time, and so we can instantly start with the production of parts without looking for tools that we need to manufacture those parts. This all leads to a true just-in-time approach, with being lean as we reduce the physical transportation of goods. There are two alternatives how AM can be applied. First of all, there's the centralized additive manufacturing production, which is more suitable today as the machines are still quite expensive to buy, and they need to operate at full capacity to be able to be economic. So we still need a lot of finishing work, so we need more machines that can post-process the parts. We have low build-up rates. That means we have to take more time into account to produce the parts. Until now, we have only a small number of suitable parts that are able to be produced by additive manufacturing, so that the demand is not that high, so that a centralized approach is most suitable. And we can have a high workload at this central point. The point on demand instead of inventory might be true in the nearer future. At the moment, we still have to have a few spare parts as an inventory and can produce the part as far as one was ordered. Here, in this approach, we still rely on shipping to the point of use, so we couldn't save here the logistic costs. The next approach is the distributed AM production. This is more or less a future approach, as there we have the opportunity to exploit all the benefits that additive manufacturing offers. But here still the technology has to develop. For example, the acquisition price has to decrease, and so that it is affordable to put more machines in different locations. We need a higher quantity of additive manufacturing suited parts so that the demand is higher. A better or higher accuracy reduces the finishing effort, and we can have only a few machines to post-process the parts. With a local point of production, we can save here the shipping costs, and so we can reduce the effort for warehousing. We have an overall lower workload, so we have a higher flexibility, as we have to be able to react to a sudden demand and delivering short-term needed spare part. If this is not the case, we still have the opportunity to sell this volume to others. So here we see an allocation of key aspects of the aerospace supply chain with AM potentials. For example, the first one, we have a high carefulness and precaution in all aeronautics processes. This is supported by the high degree of automation in additive manufacturing technology, as we can control here everything, and we can, do not have the danger of human failure, or lower one at least. In aerospace, we always try to enhance the processes to become more efficient. Here, for example, we have the possibility to vary the geometry from time to time and to optimize the product at nearly no extra costs on the AM side. And we have better and better becoming high-grade materials. We also have one point that has no connection to any other one, that is providing prerequisites for an approval. The technology here still lacks for a well-defined certification concept, but also within repair we are trying to develop such a concept that this technology will be better or easier to certificate. Then we have the flexibility. Of course, this is very well supported by additive manufacturing, for example, with the information technology, as this is a truly digital manufacturing technology. We can control all processes and get all the data online. Then, of course, we have a cost-efficient service level being supported by the potential to save resources, of course, the material and other chemicals. We can start the production order as we want to, voluntarily, because we do not have this setup time. The continuous quality orientation is now more or less under development on the AM side, as several machine producers develop this in situ monitoring system, where continuously the AM production is monitored and data is saved. This is all based on for future scenarios. So we thought there will be 4 stages of implementation. First of all, it just is another repair process, an additional one for the MRO providers. Then it will become a spare part production technology, where it is imaginable that we have a part database, something like iTunes, and licensed AM machines, and the MRO provider can build the required spare part at the point of use. The next step is that it becomes necessary for every MRO provider, as companies like Boeing and Airbus use this technology to produce aerospace parts, and so to repair those parts, the MRO provider also needs this technology. And the last step is that it becomes a vital part of MRO, as all the advantages are exploited from the aircraft manufacturer side, so Boeing and Airbus, as well as the MRO provider that used this technology to produce, repair, and improve those parts. If you want to get more information about this project, you can have a look at our repair website or at our Twitter account. That's it from my side. Thank you for your attention, and feel free to ask.
Yes, thank you. So we see it's more, even if the production of parts for aircraft industry is pretty complicated, repairing of those is much more complicated. So do we have any examples? Do we have something being done in that project where we have some parts?
Yes, we are trying to develop high batch repair for HPT shrouds. It's the name for small metal parts that are installed in the engine, and we try to repair those with a high speed, because there are, like, I think several 10,000s that bigger MRO providers have to repair each year. So this has to be really a fast process, and we are developing special tools where up to 50 shrouds fit into one build chamber. And additionally, we look at brackets where we produce them from scratch. So if one is bended or something like that, then we can produce new ones.
Okay. So what will the tool be? Is it a software tool, or how
yeah,
does it look like?
We try to enhance this whole process with developing an integrated IT tool which supports all the processes from the beginning, from the inspection throughout the decision whether we try to repair it, build it from scratch, or buy a new one, support the repair process, and of course the certification process as one of the big issues in aerospace.
Well, any questions from your side?
Yeah, my name is Andreas Schmidt, company is C.I.K, not carbon fiber plastics though. I've seen several times AOG. We deal with Airbus for ALM parts, and there's, for example, a very intriguing part where you have 50 machine hours. That's 2 days.
Yeah.
AOG, not possible to produce this in time. So my question is, what do you envision to do in AOG cases with this?
Okay, we always have to distinguish between present situation. There we still have to have some stock or inventory. But as I said, nowadays we produce in batches like 100 or 1,000 pieces at one point. And here we can have only, like, for example, 3 pieces as an inventory. And if one is required for this AOG, then the machine can produce the one within 15 hours, and we can put it on inventory. This is the current situation, as the machines are not fast enough. But in the future, there might be build upgrades that are able to produce these parts in 4 or 5 hours at the point where it is used. So we save the 5 hours of shipping, and then it might become time efficient enough to be applied.
A very, very critical question was AOG. So AOG is aircraft on ground, for you to know. So the last question.
Hello, so Jens Techkamp from Airframe R&T at Airbus Operations. One question about materials. So from the partners, I guess we are talking a lot about metallic materials.
Yeah.
Are we looking at all materials, aluminum, titanium, Inconel, or is there rather a plan to certify only a little number of materials, hoping that you can also replace the material? I mean, have a spare part from a different material than the original part?
Currently, we are concentrating mainly on titanium. And within this project, we will not certify a process or a material, but we will work out a general concept for certification. So it becomes easier in the future to get the approval for a certain material.
And I think there are different technologies you are focusing on.
Yeah, of course. So, well, it's a general concept which hopefully can be applied to more or less every metallic technology.
For example, SLM and
EBM and laser cladding technology.